getting, and so on. So I'll postpone all the practical announcements to the next talk, and so it's a pleasure to kick the Bootstrap 2025 conference with Rajesh.
Right. Well, thank you. Thank you for the organizers for inviting me to give this talk. So I'm here to present the latest chapter in the long story arc of the controlled bootstrap study of the 3D Ising CFT. And were this a very normal talk, I would have done something along the lines of this outline. So start with 3D Ising background material, what is Ising, what are the operators, etc. Then I would have done a technical deep dive on what progress we've made. And then I would have gone exhaustively through our results before finally concluding with future steps, or future work. But as I've been invited to give the very first talk, Slava very kindly shared with me a quote from the great Michael Fisher, who said, "The first lecture in a conference should stimulate rather than strain." So that's out. Should place a subject in perspective rather than delve into detail. Because that doesn't work either. Should respect the history, but survey recent happenings. Well, I guess that doesn't really work either. And ideally, should look on towards the future. Maybe this can stay. But if you all could be so kind, I'm going to be taking sort of a different tack, or at least slightly different tack in addressing this broad story. And I wanted to start with just a review of the history of this long story arc I alluded to. And I could have done it with the numbers, but that's not the most exciting talk. So I've already written the numbers out over there for our best understanding of the critical exponents, or equivalently the scaling dimensions of the two relevant scalars of the 3D Ising universality class. But our community here that we're here to spend time with has had quite a long history with this, and I wanted to ask, if I write something over here, is that visible to everyone? Okay. Okay, great. Oh, there's a camera, right, okay, there we go, okay, fine. So I wanted to give a brief visual overview of the history of the 3D Ising Bootstrap study. So way back in 2012 was the first famous paper that found this lovely kink in the space of delta sigma and delta epsilon that coincided very nicely with where we expect 3D Ising to be. Maybe I've made this too big, but and then soon after, in 2014, our community was able to isolate this whole region to a small island like this. And then in subsequent years, this got further insets and further insets, ... to get to the best known answer that we had as of this work, which is this 2016 number written here, which is those numbers written there. And I think the headline story for the 3D Ising Bootstrap has always been this really pushing the scaling dimensions, the determination of scaling dimensions to absurd amounts of precision. But I wanted to take a small self-indulgent aside here to mention that there's more than just pushing extra digits and scaling dimensions. And as I see it in a bootstrap study, there's roughly three kind of themes you can have for how you can push the science forward. So we have depth, which can correspond to, yes, more digits, more precision. Then we also have breadth, where we can access more kinds of data, new observables. And finally, if you're poetically minded, you might call this height, but I'll play it safe and call it new perspectives. And this is things that change our perspective, change how we see the Bootstrap and CFTs, etc. And our community has been very good at doing all of these in various ways, and all of these are very important for different scientific reasons. So, for example, pushing more digits of precision beyond just being very impressive has real scientific value, in that the O2 or the XY universality class, our community was able to, I'll just glibly call it, disprove the space shuttle. We were able to, using extra digits of precision, we were able to show that the experimentally determined values for critical exponents were contradictory with conformal symmetry. Breadth as well also has scientific value and a great example is the O3 or Heisenberg universality class Bootstrap, where being able to access the charge, the rank 4 tensor, our community was able to show that the cubic instability is weakly relevant. And this was done by being able to access this new piece of data by expanding the scope of the Bootstrap. And finally, for new perspectives, well, this is the most nebulous one, but it's also, in many ways, the most exciting. And I already gave an example of what new perspectives can look like. In the study of the 3D Ising Bootstrap, we went from looking for general bounds on conformal data to a kink that seemed to know exactly where 3D Ising was, to being able to isolate that 3D Ising into just a small island with a unique CFT, or a seemingly unique CFT within it. And so I'll call this kink to island, let's say, as a prototype. And I want to say, crucially, none of these are independent, and the best science happens when you mix and match all three. The cubic instability work wouldn't have happened without also being able to get the depth of precision to be able to really determine all the digits of that, of the critical exponent of the rank 4 tensor. And we wouldn't have been able to disprove the space shuttle without realizing that we can use these tools to rigorously isolate parameter spaces. So, okay, but now back to what this talk is about. In this talk, we're studying the 3D Ising CFT again with a bigger system involving a stress tensor. And I hope you'll come away from this talk feeling that I've delivered on all three of these categories. So in particular, we'll get more digits, so this work, or this talk. So we'll have more digits coming from the fact that we go from having 5 constraints to 53. So that will give us a much more precise determination of various CFT data. We also get new CFT data that we have never had access to either with the Bootstrap or in some cases not at all, namely to do with the stress tensor 3-point function, the and also parity odd operators. And with new perspectives, hopefully you'll believe me that at the end of this talk that I can also maybe shift your perspective a bit on what the Bootstrap can be. So with that said, I want to go into another historical aside, which is to say that you'll notice that in this line of progress for the Bootstrap, which started around here, this progress went until 2016, and then there's a gap. There's an 8-year gap. Why did that happen? Well, in part because, well, the 2016 work was very, very good. But soon after that work also, our community was busy studying the stress tensor bootstrap. In other words, the constraints that came from just a pure stress tensor 4-point function. And that, frankly, brought the numerical technology to its knees. It was really, really brutal. And the people who were there tell horror stories of what it was like. But that coincided with roughly the beginning of the Simons collaboration as well. And that was a big motivator for investing in the technology of the numerical bootstrap. We realized that there's things we can do, but we need to do this technology, improve this technology that underpins everything. And so I'm not going to talk about the technology in great detail, but I just want to say that in some sense this work is closing that loop of the science, which is in 2016 we noticed we needed the technology, so we put the Ising aside for a bit. We spent the last almost 10 years building up that technology, and now we're back at where it all began to push it to see just how far we can go. Great. And on the technology front, yeah, I'm not going to list much, but I'll just say that, well, we have SGPB 3.0 now. We have so much conformal block technology, so many tools that you can use to build a Bootstrap system and run them on clusters and all that. It's a really tremendous amount of work that we all have done in in this community, and that's something we should be proud of. So, with that said, I'm now going to jump straight into some results. So, I gave a picture of these islands, starting from not an island, a kink, to a smaller island, further and further insets. And you can basically think of the results that I'm going to show as being 2 more insets, 2 more layers of insets on that. Obviously, for a whiteboard talk, just drawing plots is maybe not the most entertaining thing in the world, but I will do one attempt. So here we have a very poorly drawn, this is the 2016 result. And with our new result is roughly like that, as published. No, now it's much smaller. Yes, okay, yeah. You're right, okay, hold on. There we go, okay. Yeah, so, but okay, this plot doesn't make sense without some context. So let me give when we do a conformal bootstrap, we have to take assumptions on the spectrum of various kinds. So we have Z2 odd channels, Z2 even channels, parity odd channels, parity even channels. And the assumptions we typically take are sigma and epsilon are the only relevant scalars. That translates into saying that delta sigma prime, so the next Z2 odd operator, has to be greater than 3. Delta epsilon prime, the next Z2 even scalar operator, is greater than 3. But in this work, we have access to parity odd scalars for the first time. So we added the assumption of the parity odd scalar also being greater than 3. And we added a relatively conservative assumption that the next spin 2 operator above the stress tensor has dimension 4. And that led to this island shrinking from this huge thing down to this very tiny thing. And again, this tiny thing itself is 4 layers of insets down on that in the big picture. So I'll write out our, so this is, as published, we went to lambda equals 43, numerical order equals 43, and we got an answer of, well, I'm just going to skip over that because we actually, since publication, we pushed the numerical order 1 more level. So I can give you now the best known answers for this conservative set of assumptions coming from here. 5, 1, 8, 1, 4, 8, 8, 0, 4, and now I'm running out of space. And 1.4126 252716. So relative to the 2016 result, including the stress tensor constraints, we and also pushing the numerical order to a notch higher, we're able to take a morally equivalent set of assumptions and get a factor of 100 improvement in the precision for each of these. So that's a lot. It's hard to visualize. It's hard to wrap your head around. And I wanted to say, with regards to this result, that one big winner that came out of this result that I need to mention. I promised numerology in the title. So our very own Ning Su had a prediction for delta sigma that came from around just a few years after the 2016 paper. Let me see where I want to put it. I'll put it over here. So Ning's guess was no, I'll put it here. Sorry. Ning. Okay. Ning's guess was kind of a very imaginative one, which is gamma of 1/6 plus 4 over gamma of 1/24 minus 5. Okay. And Ning figured this out by looking at the supersymmetric Ising CFT as well, and looking for forms that looked similar between the two. And he was able to come up with this prediction way back in 2016. And his guess for delta sigma is 0.51814808, just about. This is, so to be clear, because of this error bars, it's still within, it still is allowed. So imagine taking this whole giant island here and drawing like one line through it, placing a bet almost 10 years ago, and finding out that that bet basically worked out perfectly. That's really remarkable. I will have more to say about this, but this is unpublished. This is, so between the published and unpublished is about a factor of 2 improvement. But, great. Oh, sorry, here, yeah, sorry. Parentheses is 1, 1, 2, it's just 1, 2, 12. So it's it's an uncertainty of, are you asking what the numbers are, or what does it mean? Oh, okay, great. Okay, and great. So, okay, but this is all done with these relatively conservative assumptions, and we are able to get this remarkable result, and this could have been a very nice ending of a story. But there's still about half of an hour to go, so there's still more to talk about. And the thing I wanted to talk about is, well, first of all, we have more data than just these scaling dimensions. We also have determinations of, where did I put the marker? Okay. We also have determinations of yet further CFT data. So we have determinations of lambda, sigma, sigma, epsilon, lambda, epsilon, 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 lambda, t, t, epsilon, and what we call NB and NF, which are both related to the central charge. So these had been determined before already by the numerical bootstrap, and had been determined rigorously by Martin a few years ago. And we now have results that, I don't want to bore you by just writing out numbers, but suffice it to say, we have like 6 or 7 digits of this determined as well as this determined, which is a good jump in both of those. This piece of data, the TT epsilon OPE coefficient, this is a new one that the 4-point bootstrap has never been able to study before. But the fuzzy sphere had their determination, and the 5-point bootstrap done by David Poland and friends was also able to make some kind of a determination. And we're able to determine this now to be 0.9533151342. This is non-rigorous. I would maybe say this is semi-rigorous, maybe. But this is a new piece of data that we never had before that is, well, interestingly, it's in some amount of tension with the fuzzy sphere determination, which is 0.916273. That's fine. Now before, yes? No, sorry, so this is not extremal functional, this is, okay. Yeah, I should maybe say something.
So the question was, why is it semi-rigorous?
Yes, right. So for the scaling dimensions, what we do is we sample around with a given guess of the scaling dimensions, and the semi-definite bootstrap solver comes back to us and says, it's disallowed or it's not disallowed, and so that's rigorous. But when it comes to the OPE coefficients, these were scanned over using the so-called cutting surface method, which is a non-rigorous search routine. But then also, that only determines the ratios of these, and to determine the actual value, we fixed the vector in OPE space, and then maximized and minimized it. And that's the numbers we report here. So we're not guaranteed that these are necessarily the absolute bounds here and there, but this is like, in some sense, a good central determination for the OP coefficients, and it's very consistent. It's consistent with the rigorous results that Martin reported in his work. That's the sense in which it's semi-rigorous. I also want to point out these two pieces of data here, NB and NF, and maybe this is the time for me to erase. So NB and NF are they correspond to the coefficients of the two invariant tensor structures of the stress tensor 3-point function. And we chose a particular parameterization that makes it so that NB plus NF is, roughly speaking, the central charge. But this is a piece of data that we haven't actually studied before in the Bootstrap. So NB T T T plus NF T T T F. So this is actually, not only has it not been studied by the Bootstrap before, it was been studied by the 5-point, sorry, not the 5-point Bootstrap. This was studied by, you can sort of get at it with the stress tensor Bootstrap, but it's a very sort of sketchy determination that's hard to nail down. This has never been determined by... Okay. The way it was determined is you have something that looks like, if I'm remembering correctly, it was like... No? I got this backwards, maybe. Anyway, it's not important. Sorry, Peter.
I have an objection. This isn't
Okay.
sketchy.
Okay.
The error bars weren't so tiny, but it wasn't sketchy. It was fine.
Okay. Point taken. I concede my point. So we're, as far as I can tell, this doesn't have any determination from any perturbation theory or numerical Monte Carlo analysis or anything like that, this piece of data. And Bootstrap's the only game in town. And
Sorry.
Yeah?
You could, in principle, study this in the epsilon expansion, but it hasn't been done.
It hasn't been done. That's right. You could, in principle. Yeah. Right. Yes. 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 So the right. So the reason they're called NB and NF is if this were a free theory, this would correspond to the number of bosons and number of scalars and numbers of fermions. So you can then take a silly little napkin math calculation, and you can show that from our results you can show that NF over NB plus NF is equal to 1.3833683335%. So you can say that the Ising CFT is 1.3833683 parentheses 35% fermionic, whatever that means. That's just fun. That's just fun. But now, so we have this big. We have in our paper we have a big table of all these results. But these results are only to lower numerical order. We didn't get to study them in the higher numerical order yet. But there's more things we can do still, which is we sampled around this island. We sampled around a bunch of points, and we did OPE extremization calculations, and we got the OPE coefficient results out of that. But also we got extremal functionals. Extremal functionals that are unique due to the positivity properties of the crossing equations that we work with. And we can essentially reconstruct some solution to crossing, some version of the CFT to try to resolve the spectrum of operators. And this is an even bigger challenge for a whiteboard talk, because I think you all would have my head if I said we're going to spend the next half an hour writing out tables and tables of spectrum results. So I won't do that, and just say that we have lots and lots and lots of data for lots of different operators. But I wanted to highlight a few pieces of data that we hadn't seen, or rather, a few pieces of data that are interesting. So the way we did the spectrum extraction, yes, we sampled around, we have some island, we sample around a bunch of points, we extract the extremal spectra, and that gives us a giant pile of spectra. And so if this is like the index of the spectrum, and this is, say, twist, we find things that look like, in some cases, we have things that are very consistent and stable from one point to another. In other situations, we just have like sporadic nonsense. So in other words, as you go around the island, this operator appears, disappears, appears, disappears, appears, disappears. It's not really stable. And we had to do some data analysis to separate out the real operators from the fake operators. At the result of all that data analysis, we were able to figure out, say, the leading operators in each of the first 20 channels. And we were then able to compare those against perturbative expectations. So, where did I put this? Yeah, so I won't bore you too much, but this is, so here we have, let's call this spin, and let's call this dimension, which is, I guess, unusual because it means the unitarity bound goes like that. Okay. And we find for the Z2 even, parity even, that the first few operators, so for spin 2 above the stress tensor, there's an operator at about 5, let's call it 5.5, fine, close enough. Then we have for spin 3, this is a new channel we never had access to before, the odd spin, parity even, Z2 even operators. This is all the way up at 9. And then for spin 4, we have again something at dimension 4, dimension 5-ish. And the thing is that naively, you would expect an operator for spin 3 around here, which you can construct. So this operator here is something that looks like d cubed phi to the 6th. But where is the phi to the 4th operator? Where is d cubed phi to the 4th? And the answer is it gets eaten by this operator by multiplet recombination. And so it's missing from the spectrum. And the really remarkable thing that we see in the spectrum analysis is for this channel, so spin 3, Z2 even, parity even, all the way up, so from dimension equals 4 all the way up to dimension equals 9, there's nothing. This is just empty. So clean you could eat off it. It's at no point along this island does the bootstrap fall for the at no point does the bootstrap think that there should be an operator there. It's as if the bootstrap knows about the equations of motion of perturbation theory and all that, which is very remarkable and gives us a lot of confidence in our own results, as well as the results of the perturbation theory, which were tirelessly compiled by Johan, by the way, in a wonderful paper on the ON CFTs and their conformal data. So that's a win. It's very nice that it works out that way. But it doesn't always work out that way, and that's maybe the weird thing. So we then looked at the we then looked at the scalar Z2 odd, Z2 even rather, sorry, even parity odd sector. So this is actually the first, this is the first time that we've been able to directly bootstrap this in the Ising CFT. And it's remarkable because there's a very large gap that we expect from perturbation theory. So from perturbation theory, we expect this to be around dimension equals 11, which is up from the unitarity bound of 1/2. So that's huge. And if we look at the data now, so of dimension, say this is dimension 11 or so, indeed we see a really, really strong presence of a real operator in the spectrum right around 11. So we can see it directly, and it has dimension 10.92635998. Statistical error bars here. And the unitarity bound is all the way down here at 1/2. This is not clean. This is busy. There's all sorts of stuff going on around here. None of it looks real, none of it looks physical. We're at no point, so we don't think the answer is that the perturbation theory is wrong. all of this looks just chaotic and weird and wild, but the conclusion we can draw is that somehow the Bootstrap isn't seeing that that should be clean. It's not like this case where the Bootstrap knows already that this should all be gone.
Sorry, can I?
Yes.
This 11 is just a UV bare dimension, or it's already some estimate with perturbation theory?
It's already like the perturbation theory estimate. I think what happens is the next order correction vanishes. Johan would be the expert on this. Okay. Okay.
But what's the bare dimension? Is it?
11.
No, it's literally the bare dimension. That's what I was asking.
Yes, but it's also the one loop answer.
Okay.
Yeah. By the way, it's also worth mentioning that the fuzzy sphere answer, the fuzzy sphere determination of this was roughly 10.01. I think they reported this, but I wouldn't hold them to it. This is in a sort of a hard thing for them to resolve. But just to say that we're closer to the field theory expectations of 11. But why am I talking about all of this? Why am I talking about real operators and fake operators? And why am I talking about how clean this spectrum is and how dirty this spectrum is? Well, the answer is maybe the Bootstrap doesn't know enough about the Ising CFT, doesn't have enough assumptions. Maybe there's something more to be gotten by sharpening up our assumptions here. And we should sharpen up the assumptions because, well, I can show you the table if you like, but you can maybe believe me that we have 20 numbers with at least 4 digits of precision all the way up to like 9 digits of precision for various leading operators. And they correspond very nicely with the perturbation theory. So they cross-check each other, they corroborate each other. Maybe we should take that quite seriously. So now for the next turn of this work, which is, suppose now we revisit our assumptions. We started with the very conservative assumptions that sigma and epsilon are the only relevant scalars, which created roughly this set of assumptions. And this is a very conservative set of assumptions based on empirical observation that you can get to the critical point of, say, water by tuning pressure and temperature. But let's do better. And so we can replace these assumptions with a very aggressive set of assumptions. And the very aggressive set of assumptions that we took was to take, for these 20 operators, or 20 channels, we take the scaling dimension to be greater than the extremal spectrum, the extremal functional spectrum, minus 0.1. This is very aggressive for Bootstrap standards. This is putting a gap of 10.8 in the parity odd scalar. This is putting a gap of 9.3, 9.4 in the spin 3 sector. But we have determined all of these. This is really nicely resolved. All these real operators very nicely resolved. So we can have a lot of confidence that this is actually still conservative, even though it's many, many, many levels more aggressive than what we've been doing before.
And just to clarify,
yeah.
delta EFM is where you discarded.
Yes.
Just to clarify, delta EFM is where you've discarded the operators that are not stable in your sampling.
That's right. No junk. No junk. This is the cleaned up spectrum with various data analysis methods. It's too early in the morning to talk about clustering algorithms, but maybe later in the afternoon, if you're interested, I can tell you more about what we've been doing with that. But with these assumptions, we can now see what do we get. What do we get? And so for that, I'm going to now erase this.
Yeah, since you're erasing it.
Oh, sorry.
Yeah, you said that spin 3 parity even that was not known. That was not known before.
From the numerical bootstrap.
Yeah, but spin 1 was also not, right? And you
yes.
have access to that.
We don't have access to spin 1. It doesn't. Yeah, there's a few gaps left in what we have. So we don't have access to spin 1 parity even, Z2 even. We don't have access to spin 1 Z2 even parity odd as well. And we don't have access to spin 0 or spin 1 odd. So.
Because the data is just messy at this point, or there's a conceptual reason?
No, it's just there's no tensor structure that will allow it. So in the same way that you can't, same way that just with scalars you can't access the parity odd sector. The same is true here. We, with the system as we have it with sigma, epsilon, and t, we can't access these few low-lying sectors. So here I will draw. Did that answer your question?
Yes.
Okay. Yes.
Can someone pass one of the mic?
Thanks. So you just mentioned that in the Skinner Z2 even parity odd sector, you have a lot of random stuff below the physical spectrum, right?
Is it Z2 even parity odd? Yes, that's right.
Yeah, my question is that if you impose a big gap in that sector, for example, if you require the smallest operating in that sector is larger or equal to 9 or 9.9, so can you improve the bootstrap island further?
I'm about to do exactly that, but I'm going to do you one better. I'm going to say 10.8.
Okay.
So this is in now an abstract affine space to make our very, very tiny islands look a little bit more reasonable. So this is the result that comes from conservative assumptions. And is this a dry erase marker? Okay. Now with the very aggressive assumptions, we get something like that. I've done a very bad job. It's even smaller than this. Okay, this is aggressive assumptions. And so let me now write out the digits of data here. Okay, 0.5181488 0 2333. So unfortunately,
I guess we can further modify the assumption.
yes, you could. Yes, the other thing is, of course, how could this formula ever be wrong? Maybe the assumptions we've taken are too strong. But I do feel kind of strongly that these assumptions that we've taken are not haphazard assumptions. These are not reckless assumptions. These assumptions are very aggressive relative to what has been done before, but we have a high degree of confidence in these 20 leading operators. And so between the perturbation theory expectations and the bootstrap resolution of it, so we should feel pretty good that, and I should say also,
I didn't mean to interrupt, but yeah, my question was, is there some area of the island in the sampling that is more naturally close to not having the fake operators or something? Can you also read something out from this?
yeah, I mean, it would seem to say that if you get rid of these fake operators, you get forced into this corner of the island, right? In terms of delta sigma, delta epsilon space, I think it's either this end or this end.
Okay, maybe a related question. It's not. Is any point on the island still determined by the single correlator bound, or is it like way below that?
That's a very interesting question. That is a very interesting question. Yeah. So the funny thing is that indeed, well, I drew it like this on purpose. Like this bound here coincides between the weak assumptions and the strong assumptions. And if you actually follow it down, okay, yeah, it's not true that, unfortunately, with when we introduce the stress tensors, roughly speaking, it goes from looking like this to being like, so there's a finite gap here that separates the bounds. So the single correlator bound is not actually, at least at the same derivative order, it's not, no longer coincides with those bounds like that.
Thanks.
So in your 20 sectors,
Yes.
do you include spin 6 said to odd?
No.
Okay, thanks.
Yeah, it's sorry guys. Sorry to disappoint. No, it's every operator that has spin less than or equal to 5, which adds up to 20. So, yes. So,
It's because in that sector, there is perturbatively an operator which is below those detected in Simon's stuff in 2016. So potentially they could also not be detected by the EFM here, but still be below, and therefore potentially violate this minus 0.1 assumption.
So for your latest result,
yeah.
do you guys further search that in some sector you still get something random and prevent you to get even smaller island?
We haven't done that analysis yet.
But you plan to do that?
We haven't done that analysis yet. So the loop is we do, we map out the island with feasibility. Then we do extremal functionals to determine the OPE coefficients. And then we can analyze that spectrum, or those spectra, to go forward. So we haven't actually gone to that next step yet.
So if you keep on doing this, play this game, so what do you, what's a factor that you expect or you guess that could prevent you get the optimal result? I'm not sure if my question is clear.
What
so
fact, yeah.
you may keep on playing this game, right?
Yeah.
You get a smaller island and then search over this smaller island and then check.
Yeah.
In which sector you get something random and then prevent you get a smaller island, right?
That's a great question, and I actually don't know. It could be a very simple answer. It could be a very interesting answer. Why is it that the spin 3? Huh? So the question that Jean asked is, can you predict which channels are going to have a lot of fake junk and which channels are going to be so clean you can eat off them? Yeah, okay, so if Peter is shrugging, then I feel a little bit better to say that, yeah, I don't think we know.
Yeah, even though you cannot predict, but you may do some experiment, right? And you can keep on playing this game.
Exactly.
And you can get a smaller island.
Yes, you're stealing the punchline of my talk. No, which is just to say that, like, well, okay, let me finish writing out the digits here, and then I can keep going. But yeah, that's a great point that I will get to just now. 1.4.
I think the first two will stay the same.
Yeah. 2625. 25540. Okay. And well, now that I've written this out, just to say that, yeah, let's do some bookkeeping. So we started with before the bootstrap. This is the best result from before the bootstrap. There were roughly 3 digits determined. Then with the bootstrap, very quickly got to, well, 3 digits. Then, what is it, 4 digits, 5 digits, and then 7 digits. No, 5 digits, and then with our work now, we have 7 and 8 digits determined here. So, and this is a factor of 400 improvement compared to the previous bootstrap result, with the aggressive assumptions now baked in as well.
Why only spin till 5? Can you just go higher and get even more precision?
Yeah, we didn't.
And this is for free, basically, right? Because this doesn't.
Exactly. It doesn't take any more computational effort besides the fact you have to do like 2 stages of, like we determined the spectrum from the getting the island first, and then we got the spectrum, and then we kept going. Exactly. If we go to spin 6, yes. Now he was making a snarky comment that Johan would complain if we went to spin 6. No, it's okay. And yeah, but yeah. So I guess the point here is to say that yeah, we got a factor of 4 improvement basically for free, and the only reason we stopped at spin 5 was because 20 seemed like a big enough number to try to manage. And no, is that true?
It's a minor comment, but I'm afraid to talk without the mic. No, I think we were worried precisely about things like Johan's mentioning. So we felt like under 5, we thought, I think that it's like we are fairly confident that we understand that we are not missing some multi-twist operators.
Yeah, right, okay.
And such.
Is that not a reason to actually do it? It's kind of interesting because you would exclude the island at if you include Johan's spin. I don't know. You can.
Sorry,
you
can you repeat?
You can. So this is also gives you the opportunity to test Johan's statement whether an extra operator has to be included. That is.
Well, I mean, you're saying that if we were to impose a gap in spin 6 sector and then the island would disappear, then we would say, there is actually an operator there.
Right.
I mean, that could happen, but that would just confirm the thing that we expect.
Yeah.
And
but it would
if
be
this
quite
doesn't
interesting if
happen,
you then you can
the
impose that
island
there
is
is this
useless.
operator that apparently normally the Bootstrap can never see, and now it's there. You imposed it. It sounds like a new concept.
no, can never see is a strong statement, but yeah. Okay. Anyway, my point was just that there is a consideration of being able to like identify all the operators at high speeds, and that was one of the reasons why we limited this to 5.
So I wanted to say that instead of just going to higher spin, another option that's possible is there's a lot of sectors that have a very nicely resolved leading operator, and then like junk above that leading operator, before then another very nicely resolved operator after that. And a really strong example of this is the spin 4 even sector. There's this slightly broken spin 4 current, then a bunch of junk, then the next operator. And that's something that you should investigate. If cleaning up fake operators gets you all of this benefit in the Bootstrap, in isolating this island, perhaps this is the right approach. Perhaps we should be bootstrapping the bootstrap. We should take one set of assumptions, look at the spectrum, see what's real, see what's fake, use our better knowledge of various perturbation theory, whatever else, to come up with new assumptions that we can add onto our pile of assumptions to get closer and closer and closer to isolating like a single, or like resolving fully a single Ising CFT. Perhaps that's the right approach.
Do you have an idea? So most of the points that you sampled were wrong in a certain sense.
Yes, yeah.
And yet they told you this essential truth that, like, this operator that you're seeing in a specific, maybe in one of the spectrum, the points that you didn't end up excluding, is the true one. And like you got this information from the wrong points.
That's right.
Is there a reason why this makes sense?
Well, that's sort of the riddle of the numerical bootstrap, right? In that, like, we don't know if there is like a single CFT like at the core there, and the best we can do is create these finite regions. Of course, every single point in the finite, almost every region. Okay, Slava's getting a mic. Oh dear.
No, but yes. Why were they so wrong? I mean, I think one question that you are not really mentioning, but that you probably know this at the top of your head, is that these operators which you call junk, not only they're junk because they jump around, but probably they also have ridiculously small OP coefficients.
That's right.
And so having these operators with small OP coefficients which are probably of the order of 10 to the minus 7, whatever they are, it allows you to get a shift into delta sigma delta epsilon, which is of the order of 10 to the 7, 10 to the minus 8. So that's probably like, there's probably some numbers here which are of the similar order of magnitude.
That's right.
And so, yeah, those points are wrong by the same order of magnitude as the size of p coefficients of the junk operators, probably.
Yeah.
Is this correct?
Yeah, and we should expect that to be true, and we should also expect that, like, a more principled analysis than just seeing that there's junk is precisely as you say, Slava. But we did. We have for some of them. The reason I didn't bring it up in part is because we're still in the process of that analysis, and there's some technical issues we ran into that are leading us to feel a little bit doubtful of the specific OPE coefficient numbers. That's why I'm not talking about them right now. I don't want to tell you anything that's misleading.
Just use the mic, please. There are some mics around, so someone get one of the mics in that direction.
Can we throw these mics?
No.
Can you punt them? Yeah.
Hello. So this is my guess, but it could be wrong. So the problem is that if all the junk operators have a very small OP coefficient, that means their contribution to the whole crossing equation is very small. Then if you impose a gap to exclude them, it won't affect your island that much, right? So it's possible that at least a few of these junk operators in this random region, they could have not that small OP coefficient.
Yeah, that's right.
But that's a guess.
Yeah, that's right. This is both of those could be. We can both of them are correct in some sense, in that like you can ask yourself two different things, which is what are the things that would need to be there to get yourself away from the true CFT, but then you can also ask yourself what are the things that would make it so that if you exclude them, you would get a very small island all of a sudden, and those are seemingly contradictory statements at their face, but they're not contradictory because they're coming from different perspectives. Is that wrong? Okay.
Well, I mean, I think Slava's point was that.
Okay.
I think that Slava's point was that if you have operators with small P coefficients, they at this scale, right, their small P coefficients are small, but we're also talking about tiny differences in the, scale and dimensions.
That's right.
And I think the opposing point was that, well, that's not true. Some of them must be not too small. And I think from what we saw, they are all small. I don't think we did a direct comparison of orders of magnitude. Like, I don't think we compared them to what Slava said, whether they're comparable to the size of the island in this sense. I also just wanted to add that, and maybe Rajeev, you can correct me, I don't think that, yes, we do see this kind of garbage operators, but for instance, one thing that we cannot do is we can't just look at all our spectra that we have and see which of them are excluded by our new aggressive gap assumptions and conclude from there where the new island will land.
That's right. Yeah.
That just doesn't work.
Yeah, we tried that, and we tried to see if there's any correspondence between where these like junk operators are relative to the size of the island, and there wasn't anything conclusive or clear. It was sort of.
So in a sense, we don't even know if this junk has anything to do with the fact that the island gets smaller, because
it has to.
Like there are points where there is junk and is excluded by our assumptions, and the point is then excluded under the strong assumptions. But then there are also points where there is junk, or like where there isn't junk, and then that point wouldn't be excluded naively, but it is excluded in actual analysis, and vice versa. Like there are points in this final out region where we have junk, and we would think that it should be excluded, but it's actually remaining.
Yeah.
And so I think it's fair to say that we got kind of the idea of imposing these stronger gaps. We suspected that it would work, and it for some reason worked, but we don't really know why it worked.
That's right.
We don't understand which sector was the most important for us to impose the gaps in and so on.
Yep. I know I'm basically out of time, but can I just give a one-sentence concluding point, which is just, since we're here at the last little bit of the Simon's collaboration funding, and this is, you might ask yourself, what has it been good for? And certainly it's been good for some very nice trips to Brazil, but I do want to say, especially in this moment where science funding or people's appetite to fund science has been sort of shaken, that at very least, this whole story that you see here is a story that wouldn't have really have existed without like this community here. This is our thing, and you can point to anyone who knows what a number is and point to all these digits and say, we did that. That's what this was good for. So on that point, I'll formally close my talk and now open it up to questions.
So as you see in the schedule, although the talks are 1 hour, we allocated a little bit more time, so we have time for a discussion after the talk, and for more questions. So if you have more questions.
I just wanted to ask, I think there's, spin 1 was already mentioned. In spin 1 Z2 even, there's also a big gap expected, right, if I'm not wrong?
Yes, but we don't have access to that sector.
Right, so would it be worth to include in a other scalar Z2 even operator, epsilon prime, and then try to connect it to the rest by putting a big gap in the spin 1 sector?
Sorry, so include another scalar operator?
Yeah, as external operator, right? Because you need to, like that's the reason
yes.
why you don't have access to
that's
the
right, that's right, that's
right. So you would need a different operator, and then in general this would be decoupled. But if you try to impose that there is this large gap, maybe it gets connected and it's.
Yeah, I think that would very much be worth it. I'm aware of some people who had done a little bit of work on that, but I don't recall anything that came out of that. I don't think it was for lack of results per se, but that's certainly worth it.
So now that you have all this access to all this data, there is this question about the structure of the set of operators that appear in these solutions to the finite set of crossing equations, right? So in 1D CFT, we think that the solutions we get here, the extremal solutions, are just made of double twist operators, right? So do you think the same is happening here, that you can find a solution just with double twist operators of the external ones, or is it richer because here crossing in higher dimensions is more complicated?
I don't know off the top of my head. This is I sort of think of these as being very far away from a full solution, right? We've done so many truncations of various kinds that this is sort of like a hint towards what maybe a version of the true spectrum is. But yes, it is true that the double twist operators are the most prominent. And in particular, there's certain, I didn't mention it, but there's certain data that we now have access to. So the T epsilon and the T sigma and the TT double twist families, which you can understand as being triple and quadruple twist operators for the sigma and the sigma OPE, or the sigma epsilon OPE. Those we actually can see them in the spectrum. We can see some pretty clear traces of like operators there, and there's been some analysis being done on that, but I'm not great.
Yeah, but I just want to say these are a double twist of external operators, though.
Yes.
And there is, in principle, I think a good reason to think that if you study a given system in numerical bootstrap, even if you go to infinitely high derivative order, then you'll only your extremal solutions will only essentially include things which are double twists of the external guys. At least, like, it's very hard to imagine extremal functionals which would have more operators in them than would be accounted for by the double twist.
Yep.
And we don't see any evidence of the contrary, I think, at least so far.
Yeah, these were missing in the scalar bootstrap, but are present in our study.
So I guess it's nice to focus on the Ising island, but what can you say about the space of, what should I say, local three-dimensional CFT with the globals that do symmetry one and two relevant operators?
Yes. So you're asking now for the continent.
Yeah.
Yeah, so we've done some amount of, we did a little bit of very cursory work with, now that we have the setup for it, and you'll be able to see the plot for it, and maybe Slava will mention it in his talk. Yeah, we find, with this setup we're able to distinguish between a Z2 odd operator and a parity odd operator for the first time. With this, just the pure scalar bootstrap, you can't tell the difference between parity odd, like you can't tell the difference between a pseudo-scalar scalar crossing equations and a Z2 odd, Z2 even scalar crossing equations. So we find that with being able to distinguish parity odd and Z2 odd, the continent shrinks away. There's a bunch of region that basically corresponds to roughly where the Grosneva Yukawa archipelago should be. That is now fully excluded by this setup when looking at Z2 odd and even scalars. There's more to explore there, but the cursory look we saw didn't have that much structure to it. It was just a peninsula shrinking away.
So you're going to say there's only one?
Only one peninsula?
Only one theory. Right?
Oh, yes. Well, this is, it could be, yeah. It's, I'm going to be careful. But I think, did you have another question? Both, yeah.
So first, I have a comment for your last comment.
Oh dear.
maybe we can call these numbers the Simmons numbers.
The Simmons numbers.
That's what kidding. Okay, I have this question.
Good.
So previously, when people say the Ireland, we know that actually it's an Ireland for the data sigma and data epsilon. Actually, if you go to the higher dimensional parameter space for many more safety data, it's not Ireland. It's a pi. It's a type of a pike structure, right? If you consider
sure, if you consider the gap assumptions, there's like a spike, and we're basically slicing it off at the top.
Yeah. So actually, if you just go away from the plan, then you can see this island actually connected to the continent in different for some parameters, right?
Yeah.
So here, since you already get very precise safety data, so I wonder maybe you guys can use like tip-top or navigator to set that for how many parameters in the safety data set that you can get. Indeed, it's closed region, it's an island.
Yeah.
So the point is that what's the in how many dimensions in the whole parameter space that it's an island?
Yeah.
It's not connected to the continent.
I see. Yeah.
If we see that the dimension increase significantly, then maybe we can get more confidence that the bootstrap approach indeed can give us a single solution.
Yeah, that's a very interesting comment, especially.
But I don't know how much computation resource you guys need to figure this out to get this parameter.
That is also an interesting point. Yeah, this is certainly it would be very interesting because something I didn't mention here is that we found a couple of more Ising kinks. So in the pure stress tensor bootstrap, you get universal bounds on the parity even and parity odd scalars. Oh, sorry, parity odd, parity even. They look like this, and there's a corner here that corresponds to Ising. And with our results here, we can show that this corner really is actually like basically dead on Ising. And then we can look at further parameter spaces, we can look at OPE coefficients, and we find that there's yet further kinks. So you find something that looks like, and this is the free scalar, and this is Ising. Like bang on the money, that's Ising. So there's a bunch of different kinks that appear in all this new CFT data that we have access to with the stress tensor. So certainly, it would be very interesting to see, this question of what is the maximal set of CFT data that we can scan over and still have an isolated island.
Thanks.
Very good. So that we keep on schedule, let's continue the discussion during the coffee break. So let's thank the speaker once more.
Okay.
Just one very important thing, people that did not register, go register now before you get coffee. make a few quick announcements. So the way the conference works is that in the morning we are here, and we have 2 talks here of 1 hour each, plus some 10 minutes for questions and discussion. And then in the afternoon, we are in the building where we were at the registration. That building has 5 floors. There's -1, 0, 1, 2, and the rooftop. And as you will see, those that were here last time, it is improved compared to last time. It has many sofas all over. It's a very nice place that we can occupy at will. In particular, there are even chairs now on the rooftop, so feel free to use any space that you want, and during the afternoon. Including, there are 2 seminar rooms, if you don't find enough space to sit. One in the floor -1 and one in the floor +1. So that's how it's going to work, with the exception of this Friday, where this Friday, this auditorium is needed in the morning for some outreach activity of Principia. And so instead, this Friday, Friday morning, we have to be in the seminar rooms there. And of course, we don't fit in the 2 seminar rooms. So we decided to have these parallel sessions. So on Friday, we will have 2 parallel sessions, one in room -1, one in room +1. So Friday, we don't use the dome. In the afternoon, we can stay in the building in front until 7 p.m. At 7 p.m. sharp, the building needs to be empty. And because, as you will see, there's going to be someone at the door opening the door for us all the time, and that means that it's absolutely crucial that we always have our name tags. Otherwise, they'll start complaining and so on. So name tags are very important so that we can then enter and use whatever we want. That's the price to pay. So name tags all the time. Then lunch. So lunch, you have vouchers. Each voucher is worth 20 reais. There are some dates written on the voucher and so on. Ignore those, though that's irrelevant. So date of use, etc., forget about it. What matters is each voucher is worth 20 reais. And so the way it works is you can go to one of the 3 restaurants on the website. One is Kilov, a buffet place. I'm going there, so if you have never been, if you're not here last time and you don't know where it is, you can follow me. Jasmine is another option that we have this year. Connor will go there, so you can follow Connor. It's another buffet place which has, in particular, very nice vegetarian options, I'm told, but I've never been. And the hotel. So those 3 places, you can use the vouchers. Of course, if the price is like 63, use 3 vouchers and pay the rest. Otherwise, you are wasting 1 voucher for 3 reais. So try to aim at a multiple of 20 when eating. At Kilov, if you have a good plate, it will be more than 80 probably. And you should have, in case we did a mistake, you should have 4 vouchers per day if you are not a local, 3 vouchers per weekday if you are a local. And you can also use the vouchers for dinner at the hotel if you want. But it's probably, lunch probably will use up most of the vouchers anyway. The dinner, there will be a dinner on Wednesday at 7:30, and we'll give more information in the coming days. Feel free to suggest and organize informal discussions and informal talks in the afternoon. Not here, but in the other rooms. I mean, if they are small informal discussions, the other rooms that are very nice, you will explore the building and you will see, are plenty. So that's totally fine. And finally, just one obvious comment. Of course, São Paulo is a huge city, so all the usual precautions and safety tips that go with being in a huge metropolis hold. In particular here, maybe there are 2 extra particularities. Cars are very aggressive, so be careful when crossing the street, even in crosswalks. Make sure that you are not run over. And if you are going to a restaurant at night with your phone, where is it exactly? There is a chance some small kid with a bike can pass and take the phone away for free. And so just be mindful of that obvious thing. Don't be walking with Google Maps if you don't know the area. Of course, you will see people are using the phone all the time, but they pay attention before taking the phone out, so do the same. And I guess that's it. So we are starting with 4 minutes or 5 minutes late. I'll take that into account, and it's a great pleasure to have Slava continue the morning session.
Thanks, Pedro. Yeah, it's really great to be back, and I have amazing memories of I went 2 years ago, and it's amazing to see that this place is full of life and full of, full of development. They seem to be doing great. That's congratulations. And I was also, it was also very nice to start this conference with a quintessential Bootstrap talk, so I really enjoyed listening to Rajeev's talk. And I think it was very appropriate. And I think I would like to continue it with an, what you may call an anti-Bootstrap talk. So, or maybe not, maybe like we should all be friends. And so, yeah, so basically it's going to be 2 parts. And the first I'm going to talk about RG with rigorous error bars. And then, so this is going to be very general, like it's going to be some general blueprint, how you may want to do this. And then I'm going to say some words about tensor networks, because I'm not interested in tensor networks per se, but I'm interested in them because they give me a chance to realize the blueprint. And so for this very general part of the talk, yeah, so what is RG here? What do I mean by RG? So let us just be very general and imagine that we have some d-dimensional theory, some d-dimensional QFT, something like that. And so we have an action. So we have some degrees of freedom. So phi is all set of our degrees of freedom. And we have some UV cutoff, lambda. So I'm describing non-perturbative Wilsonian RG. And so there's some action that I have to parameterize it somehow. So I'm going to expand it in some set of couplings times some interactions, OI of phi. So this is all very general. And I'm going to assume that I have an RG map. And so this RG map, what does it do? It takes, so it reduces the cutoff as usual. So lambda is mapped to lambda over b. And it reduces the cutoff in such a way that the partition function is preserved. So d phi e to the minus s, so I'm going to write s lambda of phi. And so this is with the cutoff lambda, is equal to e to the minus the integral d phi with the cutoff lambda over b, e to the minus s lambda over b of phi. So this is the usual thing. And so this is the integrating out step. But as usual, we will have also, we are going to go back to lambda. So which means that we are going to now rescale the field. So we are going to add to this rescaling step as usual. I just want to make sure that everyone is on the same page by what we are doing. And so once we rescale, we are going to be going back to the same cutoff lambda, but now my action has changed. So now I have another action, S prime lambda, depends on phi. And so this rescaling step basically rescales energies back to energy goes to BE, going to BE. And so what is the physical meaning of this rescaling step is basically that I want to measure my couplings in my action. I want to measure them at the scale of the cutoff. And so since I changed the cutoff, I have to rescale everything back. And so once I did this rescaling step, lambda, I started with a certain lambda, I'm back to the same lambda. So lambda now, it doesn't really matter. I can set lambda equal to 1 if you wish. So there's no more any importance. And then this is the RG. So the RG map is, it's the map which maps S to S prime with the same lambda. And once I have this RG map, I can iterate it. I can start iterating. S1 goes to S2, goes to S3, and so on. And so this is the RG flow, and the reason why we are interested in doing these iterations is that we hope, and this often happens, that after a bunch of iterations, some simplification is going to occur. So maybe your original action is complicated, contains a whole bunch of terms, but maybe after doing many iterations, you will see, oh, well, this term is the most important one, so I'm learning something. So this was the original idea. And so in particular, you know, people like drawing this sort of pictures that you have maybe a phase diagram where there's a whole bunch of actions, and once you start iterating this, then maybe you are going to start converging to some fixed points. And there's going to be maybe this fixed point, S star A, and maybe there's going to be another fixed point, S star B. So this is very useful because you can start classifying your phases in terms of fixed points. So this is clearly very, very useful in physics. Some of these fixed points could be of some simple nature. Maybe they will correspond to 0 correlation length, like high temperature fixed point, or some more complicated, maybe topological quantum field theories. Other fixed points may correspond to infinite correlation length, so those going to be critical theories, maybe will have conformal invariance, so that's the thing. And by the way, you know, if you're only after the fixed point, then there is no need to do an iteration. So, you know, to find a fixed point, you just have to solve the equation R of S star equals S star, and that's it. You don't need to do any iterations. So in fact, you may just forget about iterations and just solve this fixed point equation, and you're already going to be learning something, right? And then once you perturb around this fixed point, you're going to learn about critical exponents, so you're going to be learning a lot of things. So this is very standard thing, but actually, you know, I was surprised to learn, actually I had some bizarre discussions with some senior physicists who are editors of GHEP and whatnot, and I realized that there are some people out there, you know, for me, this is just something that Ken Wilson wrote down 50 years ago, and this has been since then ever with us, but there are some people who don't think that you can just do a single RG step, go back to the fixed point, and this contains all the physics. And another thing that I want to draw a line between is that what I described here, this Wilsonian RG, if you do it, if you don't do any truncation, then in principle this is exact. I'm not making any mistake here. And so I want to draw a line between this procedure and perturbative RG. So there is something which is called perturbative RG, of course, and confusion is enhanced by the fact that it was Ken Wilson which invented both of these things. He actually invented first this, but then he said, well, this is hard to do, so let me just do perturbative RG. And perturbative RG is something like epsilon expansion. And of course, it works great, and it's much easier to do. So somehow people forgot that this is fundamental, and this is just something that Ken Wilson invented as a temporary fix. But the temporary fix is with us, but what he first invented is still not quite finished business, as I want to emphasize. So, the perturbative RG, of course, there's always some error involved. So, of course, unless you believe in resurgence and whatnot, which I don't, while here there's no error. There's no error, but you have to work with infinitely many couplings, right? So there are infinitely many couplings. And at this point, there is usually a mental block, at least when I talk to theoretical physicists, there is usually a mental block in the sense that people find it very hard to understand, and there is indeed something to understand. So if there is an infinitely many couplings, so it means that, okay, for any practical calculation, I will have to do some truncation somewhere. But if I will have to do some truncation, you know, people start wondering, okay, well, you do truncation, but what's your expansion parameter? Well, how are you ever going to get anything rigorous out of this if you do truncation? So there is something to be explained, in which sense this framework can be done exactly. And so that's what I would like to start with. So, so how can, sure. Yeah, this
So while we're still talking about these basics, I just wanted to ask in this non-perturbative version, should I be worried about like boundary conditions at infinity or things like how you define thermodynamic limit? And
yeah, you should worry about this. Yeah, you should worry about everything. But
in practice,
but in practice, that's not the main difficulty. Yeah, you can usually control it. Like if you can control things that are difficult to control, then this becomes a minor point. You can check.
I mean, part of the reason I'm asking is that understanding what sort of different thermodynamic limits you have by itself already has a lot of physics in it. So for instance, if you have like spontaneous symmetry breaking, then the limit is not unique, and that's already part of the answer.
Well, later in the talk, there's going to be an equation that I'm going to write down if I get there, and that could be a good moment to illustrate how you can control the thermodynamic limit, how RG actually helps you to control thermodynamic limit.
Okay, thank you.
Yeah. So, so okay, we have this, so now the next task is how can you ever hope to do this exactly? Isn't this exactness is a misnomer, right? You say it's exact, but then you have to truncate. So there is so what are you supposed to do? There is this infinite list of couplings ki, and let me split it. Let me split this list k into two sets, x and y, and so x is going to be a finite set of couplings. So it's going to live in some Rn, and I'm going to take n to be large but finite. So finite, but it may be large. You know, maybe it's like n equals 100. Depends on how strong you are, how big a computer you have. But y is infinite dimensional. So k was initially infinite dimensional, so y is infinite dimensional. So because I'm including all couplings which are consistent with the symmetry. And so I'm going to write down my RG map in terms of this parameterization. So there is a map R which maps x, y to x prime, y prime. And so there's basically two functions. So maybe I'm going to write x prime. There's some function f, which is a function of x and y prime is a function g, which is a function of x and y. And I imagine that I wrote some formulas for these functions. Maybe there are some infinite series involved and whatnot, but I'm trying to do very general considerations. And so if you have these functions, then the first thing that you may want to do, and the first thing any sensible person would want to do, it would say, well, let me just set y equal to 0, because I'm going to be optimistic. I'm going to just assume that y is small, and let's see what happens. Well, setting y to 0 means that you're going to study, instead of this full function f of xy, you're going to study a function, so x prime is equal to f of x0. So let me call this function f0 of x. And this is just some function which acts from Rn to Rn. So n is large, but it's a finite dimensional space. I presume that I have some formula for this function, or maybe I have a computer code which computes this function, so I can analyze this function. I can study this function as well as I can, and I presume that I can understand it. Like if I cannot understand even this function, then I'm finished. But I presume I'm trying to be optimistic, so this function I can understand, and for example, I can understand its fixed points. So for example, I can find a fixed point x0 of this function. So this is x0 is a fixed point of f0. And once I found this x0 fixed point, and maybe maybe I found it numerically, maybe I guessed it, you do it. Then you can also try to study the RG flow of F0 around this approximate fixed point x0. And typically, in situations of interest to quantum field theory, you will find that there's going to be a finite number. Maybe there's going to be R relevant directions, relevant or maybe weakly or maybe near marginal directions. And then the rest of directions are n minus r, and n is a large number, but r is a finite number which doesn't depend on n. So these directions are going to be, n minus r are going to be irrelevant. So the flow of F0 near this point x0 is going to look like there's going to be some surface which locally is going to look like r n minus r of irrelevant directions. And then there's going to be some finite dimensional relevant directions, so the usual thing. And once I figured this out, I can compute these eigenvalues corresponding to the relevant and irrelevant directions. They're going to be some eigenvalues lambda I. I can compute them, maybe numerically. And by the usual RG logic, then these eigenvalues are going to be related to the scaling dimensions of operators of my QFT, describing the fixed point. By the usual formula, lambda I is going to be equal to d minus delta I, so that irrelevant directions will correspond to eigenvalues less than 1, relevant to eigenvalues larger than 1. So this is the usual thing. But of course, this is just all approximate, because my lambda x0 was not a true fixed point of the full RG map. It was just an approximate fixed point. It was a fixed point of this F0. So let me call this, I don't know, this is lambda 0 I. So this equation clearly has an error in it. And so how can we understand this error? And there are some practical ways you can go around it. For example, there is this n parameter which I introduced. Maybe the first thing you would want to do, just to make sure that things make sense, maybe you want to vary n and you see what happens. So you compute this lambda I, you vary n, and then you see how this lambda I varies. And maybe if you're lucky, you will see that this lambda i's, they vary regularly as n, and maybe they converge to some value. Maybe if you're lucky, that's what you're going to see. And then maybe if you're a practical person, you will say, well, I'm just going to take I'm going to do a fit maybe when n goes to infinity, or maybe I'm just going to do some estimate of the error as the difference between the two last points that I computed, and maybe I'm going to write a paper, and but then there's going to be a Bootstrap paper which is going to beat this anyway. So, but maybe I'm not so lucky. Maybe your predictions are going to jump around all around the place. So what's going on? My method doesn't work. Was Ken Wilson wrong? What's going on? There's something badly wrong with this whole idea. Maybe this whole fixed point business is wrong, doesn't exist. Actually, you would be surprised to learn that Sasha Polyakov told me many years ago when I was still a grad student that the whole non-perturbative RG is just wrong. It doesn't exist. That there's only perturbative renormalization group. And so for many, many years, I was misguided. Thus, and so started working on CFTs and things. So, okay, so no, we want to do something better. So we want really to assign to these points some rigorous error bars. Working with finite n. So we want to somehow understand these rigorous error bars. And how can you ever do this? So typically, when I try to explain this, usually at this point, people just get blocked. And some people just say, well, no, there is this infinite y is involved here, which I truncated away. So how can you ever understand this? This is just impossible. It's impossible. Well, it is possible, so it is possible, and I want to convince you that this is possible. It's possible with the finite computation to do this. With a finite computer. So, we have to bring back this y, and so how are we going to bring it back? So basically, we hope that we made an assumption that y is equal to 0, but we hope that in the end y is not going to be 0, but it's going to be small in some appropriate sense. So what does this mean? So we have to look back at this function. So we have this equation y prime is equal g of xy, the function that I dropped. And so, of course, the key point is that even if y is initially equal to 0, then after one RG step, we get y prime is equal g of x0, and this is not in general equal to 0, so y, even if you assume that y is 0, then it's generated by the RG step, so it cannot be exactly 0. There's always going to be some y prime. But we cannot compute y because it's infinite dimensional, but we can estimate it. So we need to estimate it. And what does it mean to estimate it? Well, I don't know. In mathematics, to estimate something infinite dimensional, it means to show that the norm of this y is going to be small. So this has to be small. And what's a norm? I mean, there is there's a gazillion norms that mathematicians invented. Okay, that's the point where you have to be creative. So you can't just, you have to be creative. So you have to find what is the right norm. And there are many norms. Like, for example, okay, one typical norm that you can consider is just L2 norm, where you take all the coefficients, squared, 1/2. Well, that's one particular norm. But that's not the only possible norm. I mean, there are many other norms. There is like L infinity norm, where you just take a maximum of these coefficients, yi, and so on. Another thing that I have to point out is that, okay, I never discussed what is the normalization of these couplings yi. So there was no natural normalization involved. And so, I wrote to you y1, y2, y3, y4, but maybe I should take these couplings yi and just rescale them by some coefficients, and those coefficients are going to depend on I. Or maybe they were already rescaled because my choice was not very nice. So there could be some weight factor here also in this norm, wi, which you don't know a priori what it is. So you have to be creative. You have to find what is the right norm. And then, so you have to choose a norm. And then once two key assumptions have to be satisfied with this norm. So they may not be satisfied with an arbitrary norm, but hopefully there is a norm for which they are satisfied. So the first assumption is that if you compute the gradient of this function g with respect to y, so y lives in some space endowed with this norm. So the function g acts from this space to itself. So the gradient is a linear operator acting from a space to space. So it has an operator norm. So here, so it's an operator norm, GGY. And so this operator norm, I'm going to write it here, that it's a different norm. This operator norm has to be small, has to be smaller than epsilon, which is less than 1, where epsilon is some parameter. So what am I saying here? I'm just saying that I'm making an assumption that all these infinitely many directions that I'm not considering explicitly, that they are all irrelevant. And the correct mathematical way to formulate that they are relevant is to say that the gradient has operator norm less than epsilon. Well, epsilon is going to be some numeric, some number that you will have to compute. So notice that this computation here that I described, this could be done by a computer. This can be done by a computer. This you will have to prove analytically.
Do you need
Because
this
you will
for
have
all y or just for small y? Or
excuse me?
do you need this for all y, small y?
Yeah, I'm going to say it, so this equation has to be true in some neighborhood. In some neighborhood, let me call it u of the point x0, 0. So for example, this neighborhood maybe has the shape x minus x0 less than some delta, and the norm of y is less than delta. So you have to pick a neighborhood, and in this neighborhood, this has to be a contraction. So yeah, so basically I'm saying that there is a, this is x direction, this is y direction, this is x0 point, and so this is my neighborhood u. And so within this neighborhood, the map acts as a contraction in the y direction. So you have to show this. So this is the first condition that you have to make sure that it's satisfied. And there is a second condition, which is that when you do the first RG step, when you do, so you take the first RG step, which starts at x0, and then, as I said, it's going to generate some non-zero y. And so this generated y after a first RG step, so if, like, the first RG step is going maybe to take you from here to here, it should not take you out of the neighborhood. Because you proved that something is true in this neighborhood. If you do an RG step and it takes you out of this neighborhood u, then it's useless. So the first RG step should not take you out of the neighborhood. So this basically means that your initial approximation x0 is not a good approximation. It's a good approximation.
A silly question, but doesn't that depend on b? Can you not take b sufficiently close to 1 that that's always true?
B?
B. There is scaling lambda over b.
No, but b is not something that is at your disposal. So b is a parameter of the RG map. So b is a fixed number. It's actually usually going to be an integer number, like b equal 2.
I see, because
so changing b, it means that you change the RG map.
I see, because from a path integral, continuous path integral viewpoint, b of course could be arbitrarily close to 1, but you're saying you're doing something on the lattice.
It could be that changing b and playing with a b very close to 1 could help you solve this problem. It could be. It could very well be. But eventually, for me, b is going to be equal to 2, so I will have to find other ways of solving this problem.
Thanks.
And so under these conditions, so if these two conditions are true, then I claim then there exists this very simple theorem. Actually, the theorem requires a few other conditions, but I'm not going to write those unless you really force me to, unless you are attentive enough to see that some conditions are missing, and then I will have to add them. But these are the two most important ones anyway. So there is this theorem that under conditions 1 and 2, I can show that there exists in U an exact fixed point x star y star. So it's exact in the sense that R of x star y star is equal x star y star. And exact eigenvalues lambda I star. So these exact eigenvalues are the eigenvalues of the linearized RG transformation around the exact fixed point, just like lambda I0 were, or at least some low ones, are within order epsilon, where epsilon is the same epsilon as this one, from lambda I0. And this constant can be computed, explicit constant. And hence, rigorous error bars. So basically, what I'm saying is that given this condition on the gradient in the y direction, even though my full RG map has this G part, which acts in this infinite dimensional space, but is this infinite dimensional part of the RG map is really just, in some concrete mathematical sense, a tiny correction on this finite dimensional part of 0, and so whatever it does, I mean, I can take it into account by a tiny bit of functional analysis, which any competent mathematician studied in grad school, and so it's a tiny correction. So everything that you can possibly be interested about your map, in particular the eigenvalues which control the critical exponents, they are corrected just at order epsilon with some completely explicitly computable coefficients. And so that's it. And so this is a blueprint. So this is a blueprint for doing RG computations with rigorous error bars. And why is it still a blueprint? Yeah.
Could you give an intuition of why that theorem is true? In particular, so naively, if I'm at x0 and I'm away from the fixed point and I do an RG step, both if I'm missing an irrelevant direction and if I'm missing a relevant direction, I just go away a bit, and it looks naively like it's hard to distinguish by a single RG step if I go away along a relevant direction or an irrelevant one. So I did not understand how condition 1 excludes relevant directions.
Well, all the relevant directions are around x.
But we don't know that, right?
We know this because because this condition that the gradient in the y direction is a contraction, it means that there are no relevant directions along y.
Yeah, so can you explain that, please?
Well, relevant direction means that there is an eigenvector which has an eigenvalue larger than 1.
Okay, so it's just a 1 there. Okay.
If the eigenvalue is larger than 1, then if you pick a perturbation that eigenvalue, you act with an RG step, that vector is going to be increasing by some factor larger than 1. But this equation says that the norm of any vector is decreasing. Okay, so this equation actually excludes eigenvalues larger than 1. I mean, it excludes other things, but in particular eigenvalues larger than 1. Thanks for asking.
So you didn't see about the base of couplings. Should we include all the local terms, RG steps? Do they generate non-local terms, or?
Yeah, I was very vague about this. So this is kind of, you should include all terms which are generated by your RG map. So if your RG map somehow is very nice and generates only local terms, then you should only include those. If your RG map generates also slightly non-local terms, then you have to include also those ones. So it's up to you. Yeah.
So what if this is one or two operator that switch from x to y or come back from y to x? If such kind of things happened.
Operator switch from x to y.
Yeah, it becomes relevant to irrelevant, or from irrelevant to become relevant.
No, I'm sorry, I don't understand the question. X and y is just like.
So here you.
These are just some coordinates in your space, like, and the function acts in the space. So once you fix the choice of the coordinates, then the coordinates cannot move around. It's just some choice of basis.
But we know there could be some possibility that near in this neighborhood, one of the operator, it could be.
There are no more operators. It's just coordinates, and the map acts on these coordinates. What does it mean in terms of coordinates that x becomes y? I already said that who is x and who is y. Once I said this, they cannot. My coordinates don't jump around like cats and dogs. They are fixed.
Yeah, sure. I mean, in the neighborhood, another algebra know it's possible that one of the. Let's forget about the coordinates. Just let's focus on the relevant or irrelevant operators.
Yeah.
If in the neighborhood, if there's one irrelevant operator becomes relevant.
What does that mean? Becomes? Becomes when?
It will receive some correction, right?
No, let me put it this way. It could be that there is some unfortunate choice of what you call, because you see, here I had to choose who is x and who is y. There could be some unfortunate choice of who is x and who is y. For example, I assume that all relevant directions are going to live on x and y is only going to contain irrelevant directions. That was an assumption. If the person who tries to implement this blueprint chose things in an inefficient way, it could be that things are not going to work. Maybe there is some big irrelevant direction which still lives in y. Then you will discover that things don't work. How could you fix the problem? Well, especially if you don't know a priori who is relevant, who is irrelevant. Well, you should just increase n. You should just keep increasing n, and then if your computer is big enough, eventually your n is going to include all relevant directions, and then you're going to be in business. That's why you need a big n. So I don't think, Zhijin, that this problem that you raise is unsurmountable. Yeah.
Okay.
So, okay, I said that this is a blueprint. So why is this a blueprint? Or still a blueprint? Well, because unfortunately it turns out, even though this is all extremely natural, and I'm just imposing some very, very weak conditions, and you would imagine that it's just not a big deal to check it, and there are so many mathematicians out there.
Sorry, Slava, let me ask you one more question. So, if I'm doing it on the lattice, there are many operators, right? Many more operators that are relevant, right? So if I have like a spin or 3 spins or 5 spins, they all have overlap with sigma, right? So there are infinitely many things that I would call local operators that have projection into sigma, say, right? Will I be able to really say this guy is irrelevant because it contains always a little bit of relevant typically, right?
Well, you should pick one particular linear combinations of all these guys and call their coefficient x. And then the other directions, they will have a small overlap with the relevant directions, but most of it overlap is going to be with the relevant directions. So practically, for practical purposes, they're going to behave like irrelevant, as long as their overlap is sufficiently small with the relevant. Yeah.
Okay. But that sounds very hard to do
in
practice.
No, why is it hard? In fact, numerically, it's very easy to do. We know how to do this. We do it all the time.
Maybe for the first few, right?
For the first few. But the hope is that you will only have to do it for the first few because all the other directions are irrelevant anyway. That's the hope.
Okay.
Yeah.
Is it working? Okay.
No, it will depend on everything. In fact, I mean, this structure is very flexible, which is both good and bad, because there are many things here that you can play with, and it's depending on how you implement it, you can get better result or slightly worse result. Yeah. But for the moment, we don't have any result because the whole most RG maps out there that you have heard about, they're only good for drawing pictures, but they're not good for computing anything, and they're impractical even to do something like this, where you just increase n and compute and see what happens, let alone checking conditions 1 and 2 of this theorem. And nevertheless, I'm going to cite here, if you want to Google for an inspiring story, I encourage you to Google Lanford's proof, especially if these words don't mean much to you, Lanford's proof of Feigenbaum universality. So this is not for QFTs, this is for some other problem, but the spirit of this result is very much like what we would like to do in the QFT context. And so I'm not going to spend time about discussing things which don't work, and ask me later if you're interested what are the difficulties out there. But instead I will explain in the remaining time a framework which I think has a chance of implementing this blueprint. And so this is tensor networks.
Just to have rigorous error bars, we want to be able to make them smaller. Is there also a follow-up to this theorem that tells us we can make epsilon smaller if we make n larger?
Well, there's no guarantee, but that's what we hope for, because by making n larger, the remaining, you will be including more and more, you will be treating more and more operators explicitly, and so the things which remain, they will become more and more irrelevant, and this epsilon is related to how irrelevant the tail is, so it's going to get smaller. And another thing that you're going to be making progress on is that by making n and n larger, you're going to be making, hopefully, the error of the first RG step smaller, because you're going to be including more, and you're going to be computing x0 better and better, so y prime is going to be becoming smaller and smaller, and so you will be able to make this neighborhood delta smaller and smaller, and this will help you here, so it should be systematically improvable. But these are all beautiful dreams right now. So I will focus on 2D, and instead of actions, because I on purpose phrased the discussion in the language of actions, because that's what most people in the audience are familiar with. But I will now switch from actions to this tensor network. So these are the things which are drawn like this. So these are still local two-dimensional systems with local degrees of freedom and local interactions, but written maybe in a slightly unfamiliar way. So let me explain what this means, or how you should think about this. Like at a very formal level, what you think about this is that this tensor is just a table with 4 indices, I, j, k, l. So there is this table with of real numbers, if you wish, or complex numbers. This is the collection of numbers. And you should think of this collection of numbers morally as something which is e to the minus s of phi I, phi j, phi k, phi l. So imagine that you have some sort of two-dimensional field theory, and you divided it into squares, and you discretized everything, and you put here at the vertices of the squares, phi I, phi j, phi k, phi l. These are your degrees of freedom, and you work with the cutoff, so this discretization is allowed. And so now your action was a local action, and so now because you split all your two-dimensional plane in the squares, your action split into a sum of terms, and so I just pick out a single term out of this, e to the minus s, and this is going to be my initial tensor, which is going to represent the path integral of my system. So that's what the tensor is. And then this is the contraction of the tensor network, where I just take these tensors and I contract all the indices, and then maybe I'm going to do this periodically with boundary conditions, periodic boundary conditions. And so contraction of this tensor network is morally, and actually you can make it precise at the level of equations, it reproduces for you the partition function for the field theory. So this is really, this you can make it mathematically exact. And so this is an exercise. This is an exercise that I encourage you to try to do. And if you wish, I'm happy to discuss this offline, is to translate partition function of the nearest neighbor Ising and XY models into tensor network form. And actually, for the tensor network, for the Ising model, you will find that this tensor network is going to have bond dimension 2, and the bond dimension is just defined as a range for these indices from 1 to chi. But for the XY model, you will find that you will need infinite bond dimension. So it's interesting. And so in fact, any model can be translated into this tensor network. And if you want a more formal definition of what a tensor is, then more formally, a tensor is a map. You can view it as a map so formally, you can say the tensor A is a map from tensor product of 4 Hilbert spaces to, say, complex numbers or real numbers, where V is a Hilbert space which is spanned by a bunch of vectors, an orthonormal basis, which is in one-to-one correspondence with indices I here, which I assigned on lex I, j, k, l. So this is a formal way of doing things, but this is useful also because it allows you to talk about global symmetry of tensor networks, because global symmetry is going to be encoded in terms of invariant tensors A, which are invariant under the action of a group, where the group G is going to act unitarily on the Hilbert space V, which is the Hilbert space associated with legs. And the action has to be unitary, because if you insert here a unitary matrices, UU dagger is equal to 1, so it cancels out from everywhere, and the partition function is preserved. This is very convenient. And so, okay, with these definitions, I can give yet another definition, which is what is the tensor network Rg. So tensor network Rg is a map from A to A prime such that the partition function of the tensor network Z, A on the tensor network of size n times m, where I have here n and here m, is equal to the partition function built out of tensor A prime, where all distances have been rescaled by b. And so here, Leonardo, here, you see that since I'm doing it like this, for me b is going to be an integer. And so here I can address Peter's question, so how I'm going to access infinite volume limit. So this is going to be quite easy, because to have an infinite volume limit, I have to show that the partition function of the tensor network when n and m scales to infinity is going to, basically I have to show that this is equal in the n infinite volume limit, I have to show that the partition function z has to scale as e to the minus some volume of my lattice n times m times free energy f, which depends only on the tensor A, but not on n and m. So this would be a good infinite volume limit. And so typically it's a little bit non-trivial to show this, but if we have RG, then properties like this become absolutely trivial. Because RG tells you that after a single RG step, it allows you to write a recursion formula for the free energy of a tensor network on a lattice of a given size. It tells you that f of a is trivially expressible in terms of f of a prime. And if I'm going to have a fixed point, then this is basically going to tell me what f of a is, and it's going to allow me a one-line proof that an infinite volume limit exists. So that's going to be very nice. And
sorry, so, is the whole procedure translationally invariant in the sense that you use the same A at every step at every lattice point, or not necessarily?
Yeah, so the whole procedure is translationally invariant in this sense. Yeah, here you could try to generalize it to non-translationally invariant setting. So in fact, I would like to emphasize one point here. Indeed, when you do RG, some symmetries are manifest and others are not manifest. For example, if you do field theoretic RG, like what I discussed at the very beginning, translation invariance was manifest, rotation invariance could be also manifest, conformal invariance, which would be a property of fixed point, was not manifest. Now, when I went to this lattice model setting, tensor network setting, I sacrificed a lot of symmetries which are now not manifest. So in fact, the only part now which is manifest is a discrete translation invariance. So continuum invariance is not manifest, or translation invariance. Rotation invariance is only by 90 degrees is manifest. Conformal invariance is still not manifest. And so in such a situation, for some reason, people get a little bit nervous and they say, okay, well, if you do this and if you still solve the equation that R of A is equal to A or R of A star is equal to A star, is it still somehow going to be really a CFT, even though, you sacrificed all the symmetry? And, the claim is that yes, those symmetries are not manifest, but they're still there, and the scaling dimensions that you're going to extract, and they're still going to be the CFT scaling dimensions. That's the beauty of RG. I still have 10 minutes. Oh, that's great. So basically, we believe, and who are we? We, so this is work in progress with Nikolai Ebel, PhD student at HES, and Tom Kennedy, who is a mathematical physicist, a famous mathematical physicist at the University of Arizona. And so we have an exciting collaboration. And so we believe that the tensor network is a perfect framework. Tensor network is a perfect framework to give the first realization of the blueprint that I described. And so we have a bunch of partial results. Okay, we don't yet have a full result. I encourage you in particular to talk to Nikolai, who is here, if you want to know more about what we are up to.
Question, Slava.
Yeah, sorry.
So this equation is just one equation, right, for one number, z equals z. And A prime has many variables, right? Chi to the fourth or something. So this equation does not define A prime, right?
It does not define A prime, no,
so
uniquely.
There's now an art of choosing an A prime which is physically good. Well, there's many solutions to this equation.
Absolutely true. Because as we know, a renormalization group is a very flexible framework. There are many different renormalization group maps. So there are many different A primes which solve this equation. But the important thing here, though, is that A prime doesn't depend on n and m. That's something I forgot to say. And so that's why, you know, some people say that the renormalization group is a man-made thing, that it doesn't have the beauty of conformal field theory and whatnot. So you can view it as a drawback, you can view it as a flexibility. It's up to you to choose renormalization group thing. And as Igor Klebanov once famously quipped, you know, yes, a renormalization group is a man-made thing, but it's good that somebody made it. So in the remaining time, I'm going to tell you a little bit, you know, what are the great features of this approach, but I'm not going to be able to certainly convince you why we are going to be able to pull this off, but hopefully in a future conference back to the renormalization group, which has been planned at the Perimeter Institute, we will be able to present our work. So what are the great features of this approach, of this tensor network RG approach? The first thing is that locality is preserved because roughly speaking, very roughly speaking, these tensor network renormalization group maps, they look like A prime is going to be basically equal a contraction of 4 A's, with each other. And let me put here some quotation, very important quotation marks, because this equation is not quite true. I mean, this, in fact, it requires some very important modifications. But basically, A prime is going to be given by some operation performed locally on some portion of the network. So you can really figure out what your new A prime is by looking at a finite subset of the network. And so in particular, you know, we have this property that every A speaks only to nearby A's in the original tensor network. After you're done performing the Ajita summation, A prime is going to again talk only to 4 A primes nearby, and they're not going to be some A prime talking to another A prime 10 lattice sites apart. In fact, this is very important property of locality. And this is not true for other RG maps. So sometimes you have an RG maps where you start with the nearest neighbor interaction, and then you do an RG step, and you have some spin talking to a spin a million lattice sites away from it with an exponentially small interaction, but it still talks to it. So this is not nice. So this is one nice property. The bond dimension is infinite. Well, you start with, like, okay, what it means is that initially when you translate the Ising, you get this tensor with bond dimension 2, then you pad it out with zeros everywhere so that the phase dimension is infinite. Then you start taking with RG map, so the bond dimension is infinite. So you are developing some tails, but those you're developing some tails, but in this bond dimension space. So there are two different tails that you may develop. You may develop this tails in the bond dimension space, which means that you're adding some degrees of freedom, which are still localized here near this point, but they interact very, very weakly with everyone else. But at least in space, they are localized exactly here. So those are tails that you can live with. But the tails, which tell you that this spin interacts to another spin very far away on the lattice, like non-locality in space, those are really, really annoying tails that I really would not like to deal with ever. So, and this we can avoid with this approach. Yeah. No, it has to be exact, otherwise it has to be exact. Excuse me?
So I want to make sure, because this is new to me. So first point is that this equation, ZA equal to Z prime, when you solve the A prime from this equation is not exactly
it is exactly
solved by A prime, or it is exactly solved by A prime.
It is exactly solved. It has to be exactly satisfied for any n and m.
Sorry again. So when you solve the A prime from this equation,
no, you don't view this equation as an equation to be solved for A prime. You have to find an RG map.
Oh, it's a constant.
So that this equation is satisfied.
So the question is that it is satisfied exactly.
Exactly satisfied. But why are you surprised?
Because they have Fourier variables.
But that's the definition of the RG map. The RG map has to preserve the partition function. What's so surprising about it?
I mean, technically.
Exactly. Has to preserve.
When you do this computation analytics on system, so for example, you have on computer, you have like 8 times 8.
No, Zhijin, I have like 2 minutes left, and Pedro is getting nervous. So let me get to my point, and then we can discuss offline. Do I still have 2 minutes, or not really? I really have two more equations to write. So do you have time to write more? 5 minutes? Okay, that's very generous. Thank you. Zhijin, you can ask your question. Okay, so another very nice thing is that there is some connections to quantum mechanics. So usual RG is a little bit disconnected. So there's quantum mechanics and quantum information. And so where does this connection come from? So one part of connection is that there is an ability to rotate the basis of U, or the basis of V basis. So as I said, everything is defined with respect to unitary transformations on V, which leave the partition function invariant. And this feels a little bit like quantum mechanics, because in quantum mechanics you can write equations like, okay, you define 0 as a linear combination of plus and minus square root 2, and so this defines for you a new set of degrees of freedom. This is the usual plus. And in usual RG, for example, you insist that your partition function has to be written in the Gibbs form, so it has to be written as a path integral of e to the minus s. And so in particular, the tensor A that you're going to get initially is going to be a non-negative tensor, a positive tensor, because e to the minus s is a positive number. Now, once you allow yourself performing these unitary rotations of the bases, you lose positivity. So in principle, you get a tensor A. After rotation, it may not be positive anymore. But of course, in quantum mechanics, it doesn't really matter. The positivity doesn't play such a role. While in probability, which is the basis of latest models, it does play a role. So that's why I'm saying that here you're kind of getting away from probability theory and positive measures to the world of quantum mechanics. And you can view it as a resource, or you can view it as a nuisance. I see it rather as a positive thing. And another thing that you are allowed to do, actually, you have to do, is something which is called disentangling. So there is a notion of entanglement here, and there is a notion of disentangling, which appears when, so you are allowed to take, you have to, it turns out. So when you perform these RG transformations, when you contract tensors AA, like pairwise, and then you're allowed to perform unitary changes of the basis on V tensor V on 2 legs, not on a single leg like in the first point that I described, in a way that you are going to simplify this contraction of 2 tensors. So you're going to find 2 tensors BB, which are in a sense simpler than A, or rather that the entanglement between B is smaller than the entanglement between A, and this sort of operation allows you to filter out some junk from your tensor network, and that's very important for getting successful RG transformations. So that's a nice point. And the third, maybe last, no, there are 2 more nice points. So the next last point is that there is a natural choice of norm. So I told you that this choice of norm is a little bit of a pesky issue because you don't know, like, normally what is the normalization of the couplings. You don't know what is the norm. Maybe you should take LP norm, weighted norm, and it's like a gazillion norms in mathematical books. Which ones should you choose? But here, this framework, it comes with a God-given or goddess-given Hilbert-Schmidt norm. So the normalization is fixed. So actually, the norm that you should choose is where tensor elements squared 1/2 without any weight. Without any weight here. And that's interesting. So because this norm behaves naturally, it behaves nicely under contracting tensors, and when you form tensor networks, you contract tensors. So somehow you don't have any ambiguity, like what kind of norms you have to work with. So that's nice because there's one less thing to worry about. And then finally, the last nice point is that at a numerical level, at a purely numerical level, this thing is known to work. So there are existing numerical algorithms, and they go back to the work of Levin and Nave from 2007, and then there was also an important work by Pedro's former colleague Guifrey Vidal and Glenn Evenbley back in 2014. And so these existing numerical algorithms, they implement what they called F0, and they show that you can get excellent results, at least at the level of truncation. So if you increase n, I had a plot there where you increase n, you see that things converge as far as F0 is concerned. And so basically, this gives us hope. These existing numerical algorithms, unfortunately, they have some steps in them which don't marry so naturally with the Hilbert-Schmidt norm. So we can't use precisely their algorithms. We have to be a little bit inventive and modify those algorithms. But by and large, we think that the existing numerical evidence gives us hope that this is going to work. So I think that's now you know what we would like to do. You know a little bit the keywords of how we plan to do this. So just wait for another year or so, and then hopefully you'll see a paper on the archive. Thank you.
Hi, Slava. So in the curve T, we know that when we do the RG operation, we will lose some information about the UV, right? So here in the Tensor work, could you tell us that in which step in your computation you lose some information about UV, and in which way?
You lose information about UV.
Yeah.
So
in which step and in which way we?
Well, in this step, which is the only one that I make.
But you mentioned that this is an exact mathematical exact equation, right? If it's mathematically exact, then I guess you don't want to.
No, the equation is exact, but now the mathematical equation is exact, but the physics, what is the physical consequence of this equation? The physical consequence is that A prime and A belong to the same phase. They describe the same phase, and the phase is the infrared concept. So of course you're going to lose some UV information. Now, you can, if you look at some specific details in how the RG is realized, you can write some other equations which I haven't written, which will tell you that, for example, correlation functions, some correlation functions at distances larger than a certain distance computed with tensor A prime are going to be the same ones as the correlation functions computed with tensor network A, but only beyond a certain distance. So again, you're losing some information there, but only about the UV. So this is just, yeah, it's just the usual RG. I don't think. The nice thing here is that we don't have to reinvent the wheel. This is all in the textbooks, in Ken Wilson's papers. The philosophy is all there. We don't modify any philosophy. Fully what Ken Wilson said. Let's just finish this, because Ken Wilson had great vision. He was also a very powerful man, but people who came after him were not as powerful. So.
Maybe one question about an application. What is the status of using this to prove the absence of a virial current in the CFT, in the possible CFT?
Connor, this is what I would call RG step, which takes you out of the neighborhood of what I was saying. So we should discuss offline.
Let's thank Slava. Let me just make a